Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to tackle the topic of surface area of revolution in parametric equations. It's a big, long title, and really we've made a natural progression up to this point, and let me review that now. We've talked about in regular functions, Cartesian functions, we've talked about the arc length, we've talked about that. Then we moved on and we talked about the surface area of a function that you rotate about the x-axis in Cartesian coordinates. Then we took a break and we talked about these things called parametric equations, which are just functions that instead of having f of x, you have x of t, which is the parameter t, and y of t. Okay? Then we talked about the arc length in parametric equations, which was derived very similarly. And then here we're going to complete the circle and we're going to talk about the surface area of revolution in parametric equations. And you're going to see that it's very simple to follow by analogy to get this equation, and it's pretty simple to use it. So, recall that the area of a surface of revolution is the integral, and this is Cartesian version, from a to b, this is reviewing what we already know, is 2 times pi times f of x times the square root of 1 plus f prime of x squared dx. So you're integrating over x, and this is something that we derived a long time ago. This is the surface area of revolution there, okay? And recall, just to spell it out for you, that this part of it right here, this was the circumference of a slice, okay? Of a slice of that cross section. I'll draw it for you here in a second. And this part was the length of the curve. That's what it was. So basically, to draw it for you here, if this is x and this is y, this is some arbitrary function. Okay? So what you're going to have is you're going to rotate this guy around. This is the function, and you rotate him around, and at every value of x here, you're going to have a cross-sectional slice, and this cross-sectional slice is going to have a circumference, okay? And that circumference is 2 times pi times f of x. F of x is given by this thing right here. The length of the curve is already given to you from the previous section. You put those together, you integrate, and that's what we already talked about in the previous sections was the area, okay? Now, I'm going to write down the corresponding version in parametric equations without any proof at all, and we're going to look at why we think it's true. The surface area of revolution in parametric equations is the integral from alpha to bravo, so it's just the integral over the limits. Okay, let me write it down and we'll talk about it. 2 times pi times y, in this case, it's y of t, just because we're talking about parametric, times the square root of dx dt squared plus dy dt squared integrated over dt. Now let's look at what we have here. This part should look very familiar to you because from the very last section here, the one right before this one, this is the length of this curve when you have parametric equations, x of t and y of t. You take these derivatives, you plug it in, and we integrate, that's the length. This, I'm claiming, is the circumference of a slice. So looking back above, it's exactly the same form as this one. This is the circumference of a slice when you're talking about regular functions, and this is the arc length in regular functions. Down here, we're just using the corresponding versions in Cartesian. This we derived in the last section, and this is the only thing that I think needs explaining. 2 times pi times y. Well, in parametric version of coordinates, you have a function, x of t, which is a function of that parameter t, and y of t. So what I need to do at every slice is I need to know the circumference, okay? So this distance from the axis up to the curve is y of t, because that is the equation that tells me what the value of y is as I march along in time. So it's 2 times pi times y in parametric coordinates times this length that we already just derived last time. It's very simple to apply it. All you need to know is your x of t and your y of t. Take your derivatives, square them, put them in here, put your y in here, and then you go ahead and do your integration, and that's how you do the problem. So we're going to do that right now. The first problem, okay, so the first problem is going to be x is equal to 1/2 t squared, and y is going to be equal to t, and the parameter t is only going to vary from square root of 3 all the way up to 2 times the square root of 2. So it's a kind of some wacky limits, but That's the way they are. It goes from square root of 3 up to 2 times the square root of 2. This is my function defined in terms of parametric equations because t is my parameter, time, basically. So the surface area of this function, if I revolved it, would be the integral from alpha to bravo. I'm just going to write it down. 2 times pi times y times the square root of dx dt squared plus dy dt squared dt. This is just what I wrote on the last board. So obviously, in order to do this, I need to know what these derivatives are and the square. So let's go ahead and do that now. dx dt is equal to, looking up here, it's 1/2 times the exponent 2 times t. Exponent minus 1 is going to give me 1. So that's going to be equal to t. Okay? We need to know what the squares are. dx dt squared is equal to t squared. Okay? Now, what about dy dt? dy dt is going to be very simply, taking the derivative of this is 1. Okay? And then finally, that means that dy dt squared is equal to 1. So I got some pretty simple things. dx dt squared is 1 and dy dt squared is 1. So let's go ahead and put them into the relation for the area and see what we get. We're integrating from alpha to bravo, which is square root of 3 to 2 square root of 2. So it's square root of 3 to 2 times the square root of 2. We're integrating that. And what we're integrating is 2 times pi times y. Y is my function, so it's just t times the square root. dx dt squared is t squared plus dy dt squared is 1 dt. Okay? dt. So that is what I need to integrate. There's really not much I can do inside of here to simplify it or factor it or anything else. I really can't do anything there. But if I notice right away, I can do a substitution, right? Because if I make u equal to t squared plus 1 and I take the derivative as I do for all the substitutions that you do, derivative of t squared is t. So that's going to end up canceling with this t and I'm going to have a nice integral in terms of u. So let's do that. u, let's go ahead and try it, t squared plus 1. So that means that du dt is equal to 2t. Derivative of t squared is 2t plus derivative of 1 is 0. Okay? And that means that dt, which I'm going to need to plug back in here, is equal to 1 over 2t times du. Okay? So let's go ahead and try our hand at this substitution. Integral from square root of 3 to 2 times the square root of 2, okay, of 2 times pi times t times the square root of t squared plus 1, but I define that to be u, okay, times dt, but I found what dt was, 1 over 2t du. And now you see why we did it. This t cancels with this t, and now you just have an integral in terms of u and du, and this is a simple integral to evaluate, so that's good. Now look at also here what happens is, in addition to this t canceling with this t, this 2 cancels out with this 2. So this integral actually becomes a very nice integral. It just simplifies to be integral of square root of 3 to 2 times the square root of 2. And the inside I'm just going to have my pi times u to the 1/2. I'm just going to write it in terms of u to the 1/2 because I always like to do that with my integrals, times du. Okay? Times du. And that's a simple integral to evaluate. Okay? All I'm going to do, this is a polynomial integral, it's going to be pi over exponent plus 1. 1/2 plus 1 is 3/2, so it's going to be pi over 3/2 u to the 3/2 because it's exponent plus 1, and I'm going to be evaluating this thing from square root of 3 to 2 times the square root of 2. Okay? Now, obviously, these limits are in terms of x, but I still have my integrand in terms of, or what I've integrated here in terms of u, so I'm going to go ahead and substitute what I know u is, and I'm going to simplify this. So when I flip this fraction over and multiply, it's going to be 2 pi over 3, okay, 2 pi over 3, times u, which is t squared plus 1, t squared plus 1, all raised to the 3/2 power, and finally integrated from square root of 3 to 2 times the square root of 2. So the final thing I'm going to get here is 2 times the square root of 3 t squared plus 1 to the 3 halves integrated over my limits from square root of 3 to 2 times the square root of 2. So I'm going to continue over there, and we're going to do that. Now let me go ahead and write down what we found just a minute ago so that we can stay together. 2 pi over 3 times t squared plus 1 to the 3 halves evaluated from square root of 3 to 2 times the square root of 2. That's what we had, okay? And let's go ahead and do that. We're going to have 2 pi over 3, and we're going to evaluate this from the top limit to the bottom limit. So what you're going to have here is 2 times the square root of 2 squared plus 1, and you're going to have this to the 3 halves power. Notice I just took this, put it into the t squared plus 1, and then I had to raise the whole thing to the 3 half power, minus, now let's do this one. I'm going to have I'm going to have square root of 3 squared plus 1 to the 3 halves. Okay. So I just plugged in the top and plugged in the bottom. Now let's go ahead and crank through it. 2 pi over 3. Now what do I have inside of here? What do I have inside of here? Well, this is going to be 2 squared is going to be 4 times square root of 2 squared is going to be 2 plus 1. And this is going to be raised to the 3 halves power. Okay. Let me make sure and keep my brackets here. I've got a lot of brackets going, okay? And then I'm going to be subtracting off square root of 3 squared is obviously going to be 3 plus 1 to the 3 halves, like this, okay? So it's going to be 2 pi over 3, and on the inside what I'm going to have, 4 times 2 is 8, plus 1 is 9, so it's 9 to the 3 halves minus 4 to the 3 halves, okay? Like that. So what's this going to be equal to? It's going to be 2 pi over 3, okay, times, what is 9 to the 3 halves? Well, it's 9 cubed, and you take the square root of it. Or you could say 9, take the square root of it, and then cube it. Well, the square root of 9 is 3, and 3 cubed is 27. So this is 27 here. And working on this one, square root of 4 is 2, but 2 cubed is 8. Okay? So I'm going to have 27 minus 8. 27 minus 8 is 19. Okay? And finally, 2 times 19 is going to be 38 pi divided by 3. 38 pi divided by 3. 2 times 19 is 38 pi divided by 3. Okay, so let's go ahead and that's the answer, 38 pi divided by 3. Let's go back and review everything and make sure we have it all. This is our parametric equation that defines x and y in terms of variable t. This is the relation that talks about the surface area of a revolution. It's the circumference of a slice times the length. That's what we're doing. We take the derivative of x, we got t, and we take the square of that, that's t squared. Derivative of y is 1, we take the square of that, so that's 1. Going back to the formula, 2 pi y was t, times the root of that stuff is going to give us this. And right away we could see we could do a substitution. U is equal to this is going to end up canceling. We do our u, find out what dt is, plug it back in. Sure enough, t cancels with t, 2 cancels with 2. We're left with a nice simple integral, pi times u to the 1/2. We integrate that, and we have to evaluate at these goofy looking limits of integration. We plug our u back in. So we have our relation in terms of t and in terms of our limits of t, which are again duplicated up here. It was just tricky to crank through the final steps because you had t squared plus 1 to the 3 halves, and then both limits of integration had radicals. So you just have to really keep it straight with your parentheses. You have 2 pi over 3, giant brackets, and then you have 2 times the square root of 2 squared plus 1 to the 3 halves, and then minus the bottom limit. You crank through it all, and you're going to end up with 38 pi over 3. So that is the surface area of that function if we were to revolve it around the x-axis. Okay, now the next problem is x is equal to cosine t squared, okay, and y is equal to sine of t squared, and t, in this case, is going to go between 0 and pi over 2. So t goes between 0 and pi over 2. So this is my parametric form of the equation. Now we know we're going to have to find the derivatives of these. We know we're going to have to find the squares of those derivatives. So let's go ahead and do that right now. So dx dt, what's that going to equal? Well, you have cosine squared, so it's going to be 2 times the cosine of t, and the exponent minus 1, 2 times cosine of t, times the derivative of the inside. Derivative of cosine is negative sine of t. Okay? Now dx dt squared is dx dt squared is all of this stuff squared. Negative times negative gives me positive, so it's going to be 4 times sine squared t times cosine squared of t. Okay? And it's going to be very similar for y. dy dt is equal to 2 times the sine of t, exponent minus 1 gives you 1. Derivative of sine is cosine of t. And then we're going to take dy dt squared, because we know we're going to need that in the problem. Squaring this is going to give us exactly the same thing. 4 times the sine squared of t times cosine squared of t. Okay. Now what we're going to do now that we have all the information is we're going to plug it in to our formula, which is integration from alpha to bravo, 2 times pi times y times the square root of dx dt squared plus dy dt squared integrating over dt. Okay? Now we have these things. We just calculated them, so let's go ahead and put them in. Integral alpha to beta is 0 to pi over 2. 2 pi y. Y is given as sine squared of t. Okay? Now under the radical, I have some interesting stuff because dx dt squared is given by this, 4 times the sine squared of t times cosine squared of t plus dy dt squared is the same thing. We just calculated that. 4 times the sine squared of t times cosine squared of t. And I'm integrating all this stuff over dt. Okay? So, inside the radical I have 4 times sine squared times cosine squared plus 4 times sine squared times cosine squared. So I can definitely simplify that. It's going to be integral from 0 to pi by 2, 2 pi sine squared t, and then under the radical is going to be 4 plus 4 is 8 times sine squared t cosine squared t. And I can make that integrating over dt. Okay? Now, under the radical is kind of nice because I've got sine squared times cosine squared. I can take the square root of both of those, just getting rid of the square terms. The square root of 8, you should remember, is 2 times 4, and then 4 is 2 times 2. So here's the 2 that comes out, so it's 2 times the square root of 2. That's what the square root of 8 is. So I've got everything I need to get rid of this radical, and that's very good. You should be happy when you see something like that. You're probably on the right track. Integral 0 to pi by 2, 2 pi times the sine squared of t. I haven't done anything but rewrite this stuff. This is going to be square root of 8 is going to be, let me go ahead and put some parentheses around this. It's going to be 2 times the square root of 2. That's what we just found out. Square root of 8 is 2 times square root of 2 times square root of sine squared is sine of t, and the square root of cosine squared is cosine of t, dt. Okay, so I still have to integrate it, okay, but I got rid of the radical, so that's really, really nice, okay. So let's go ahead and continue simplifying. I can take some of these constants out. 2 times 2 is 4, so it's going to be 4 pi times the square root of 2, all coming out of the integral, and it's going to be the integral of sine squared t times sine of t times cosine of t, dt. Now your job at this point is to figure out how to integrate that thing. Okay, so your job is to find out how to integrate that thing. Now the first thing you want to do is see if there's a quick substitution you can do. Can you substitute u is equal to sine? Well, you could do that. You would take the derivative and cancel with the cosine, but that doesn't really leave you with that much. Okay, there's a lot of ways to probably do this thing, but the way I like to do it and the way I did it is what you can do is you can rewrite the sine as 1 minus cosine. So it's going to be 4 pi times the square root of 2. And basically what we're going to do is we're going to apply one of our tricks back from 3 or 4 or 5 sections ago on the trigonometric integrals. We're going to apply one of our tricks. This integral is going to be 0 to pi over 2. I'm going to rewrite the sine squared as 1 minus cosine squared of t. Okay? And then I'm going to keep the rest of it. Sine of t and cosine of t and dt. And you're going to see why I did that there. Go back to that section on trigonometric integrals if you don't quite understand why I'm going to do that. Now what I'm going to do is I'm going to have u equal to cosine of t. Because when I do u is equal to cosine, I'll take the derivative, it'll be sine, it'll cancel with this sign, I'll have a u squared here, a u here, I'll cancel with the sign, and I'll have an integral all in terms of u, and that's exactly what I want, okay? So, what I'm going to do is I'm going to go up here and I'm going to say u is equal to cosine of t, which means that du dt, derivative of cosine is negative sine t, okay, which means that dt, which is what I'm going to need to plug in there, is equal to negative 1 over sine t du. I'm going to need that, okay? So let's use it, okay? I'm going to have 4 pi times the square root of 2, okay? All I'm doing is I'm coming down here and I'm 4 pi square root of 2 integral 0 to pi over 2. Okay, and we said that cosine, u is equal to cosine, so it's going to be 1 minus u squared, because I had 1 minus cosine squared, times the sine of t, which is what I'm hoping to cancel, times cosine of t, but that's now u, because that's what my substitution is, times dt, but I just found that dt was negative 1 over sine t du. That's what I did there, and that's exactly why I did it, because this sign cancels with this sign. Now I have an integral only in terms of u. Okay, only in terms of u. So, let's simplify this stuff. 4 pi square root of 2, okay, integral from 0 to pi over 2. Now let's distribute this stuff in, okay? Don't forget you have a negative here, okay? So, what you're going to have is u times 1 is u minus u squared times u is u to the third power, and you're going to have times minus 1 du, okay? So what I'm going to do next is I'm just going to do a little bit of rewriting. I'm going to take this guy out. I'm going to say negative 4 pi square root of 2 integral 0 to pi by 2 of u minus u cubed du. We just took the negative out. That's all I did. Now this is really easy to integrate. This is just a polynomial, so it's negative 4 pi square root of 2 times integral of this is 1/2 u squared, and integral of this is negative 1/4 u to the fourth, and I'm evaluating from 0 to pi over 2. 0 to pi over 2. Now, of course, this is in terms of u, and my limits are in terms of x, but I'm going to fix that in just a second by substituting in what I know for u. Okay? By substituting what I know in for u. Okay, so what I'm going to do now is I'm going to do that. That's going to equal negative 4 pi times the square root of 2. On the inside, I'm going to have 1/2, okay, times u squared. U is equal to cosine, so it's cosine squared of t minus 1/4, and u again was cosine, so it's going to be cosine to the fourth power of t. Now, finally, from the limits of 0 to pi over 2. Okay? Now, finally, from the limits of 0 to pi over 2. All right, so now I'm going to go and just evaluate this guy from 0 to pi over 2. I'm going to have negative 4 pi times the square root of 2, and I'm going to have a bunch of stuff on the inside here. I'm going to have 1/2 times cosine squared of pi over 2. I'm not even evaluating it yet, I'm just writing it down, minus 1/4 cosine to the fourth power of pi over 2. Okay? That is the first major term, and I'm going to subtract off of it, just going on to the next line, I'm going to subtract off evaluating at 0. So it's going to be 1/2 times cosine squared of 0, okay, minus 1/4 times cosine to the fourth power of 0, and finally that's it. That's the whole enchilada. So it's going to be minus, there's a parentheses right here and right here, because I'm subtracting off, because I'm doing my limits of integration, subtracting off 1/2 cosine evaluated here at 0 minus that. Okay, so that's kind of ugly, but these cosines are going to really become easy to play with. So negative 4 pi times the square root of 2. Now let's go ahead and start evaluating them. Cosine of pi over 2 is 0. Okay, cosine of pi over 2 is 0, so this is just going to be I'm just going to write it down as 0 minus cosine pi over 2 is 0. So I've got a big fat 0 in the first spot. And on the second spot, 1/2 times cosine 0 squared. Cosine of 0 is 1. 1 squared is 1. So this is just going to be 1/2 minus. Again, this is going to be 1. 1 to the 4th power is 1. So it's going to be 1/4. 1/4. Okay? Okay, now continuing our simplification, it's negative 4 pi times the square root of 2. And on the inside, this is just 0, so I'm going to have a negative sign here. And on the inside here, 1/2 minus 1/4, you should know is 1/4. Negative 1/4, because I have a negative sign out there. Negative times negative gives me a positive. 4 divided by 4 gives me 1. So in the end, it's pi times the square root of 2. And that is the final answer, pi times the square root of 2. Now let's go back and trace through, because this is quite a bit of math. Let's see what we did. Here's our parametric equations, going from 0 to pi over 2 in terms of our t. We took the derivative of both of them, and we squared both of them, and it just turned out, by the way these functions are defined, that we get the same thing. So the surface of revolution, the area of it, and actually I put an L there, that should be A, because this is the area of a surface of revolution, is integrating from the limits 2 times pi times y, which gives us that circumference, times the length as defined in the parametric equation. Okay, so 2 times pi times y, which was sine squared of t, and then we put everything that we knew under the integral, the squares of the derivatives, and then it turns out we could actually take the square root of this, which is nice because that radical goes away. The 8 gives us 2 squared root of 2, and the squares just disappear from this other stuff here. We got down to this point, and then at this point you start playing with it and trying to find different substitutions. And what I did is I rewrote sine squared as 1 minus cosine squared. That comes from the identity sine squared plus cosine squared is equal to 1. I rewrote that, and then I chose a clever substitution, u is equal to cosine, so that when I would take the derivative of it, I would get sine, cancel with this sign, and that would leave me with a nice integral. So u is equal to cosine, and dt is negative 1 over sine of t. So when I rewrite my integral, I have this stuff out front, 1 minus u squared, because it was cosine squared, times sine times cosine there, and then I put that in there, and I have dt is 1 over sine. That gives me my nice cancellation. I have a nice integral in terms of u. It's just a polynomial integral, and then it's just tedious. You have to do the integration, make sure you get the right answers, plug what you know back in that you had defined for u, and then when you finally get this expression, you just have to be really careful evaluating from 0 to pi. Plug in pi in both places, subtract off, plugging in 0 in both places, and just evaluate everything methodically, keeping all of your signs straight, and you get pi times the square root of 2. So this section we focused on the surface area of revolution in parametric equations. We've completed full circle. We've talked about the arc length and the area of surface of revolution in the regular coordinates, the regular equations, f of x, etc. We talked about parametric equations, and we talked about the arc length and the surface area of revolution in parametric equations. So now you know how to find the length of a curve or the surface area of some curve that's revolved around an axis, no matter if that function is defined in terms of regular f of x that we're all used to dealing with, or if it's defined parametrically, which just means that its coordinates are dependent upon some third parameter, usually t for time, and they're independently described by that variable there.